an example of frequency domain bounce diagram in more detail. And if you guys read that, I have an example in my chapter on Scholar that goes through the whole thing and proves that the expression you get from the frequency domain bounce diagram are the same expressions that you get if you were to solve the problem in the normal classical way. Right? So please go through that example and look at the geometric series that results and how it adds up. I'm going to do the Thevenin's problem that way. I'll show you that. But I may do a few bounces here just to add to this. All right, you got this one thing?
Yeah.
We'll give it another minute or two so it won't go by very quickly. I guess you guys can always freeze the film and put the movie on. See that? All right, so I'm going to redo this now with a few bounces using the rho and showing you the difference between rho and gamma again as I go through the bounce diagram. So here's my bounce diagram. Here's my rho 1, here's my rho 2. And if I were to assume a signal of the intensity 1 starting here, that signal goes and bounces off here, comes back, a component transmits, bounces off here, comes back, reflects off this one, and a component transmits, same thing repeats. All right, that's good enough. We're going to stop here. So it looks like I need a rho 3 here, because I'm going to be bouncing off that. To really finish my bounce diagram, I need to express rho 3. So rho 1 is equal to Z1 in parallel with Z naught. I forgot which one is Z naught 1 and Z naught 2. Z naught 1 is the one on the right. And Z naught 2 is 0. So in parallel with Z naught 1 minus Z naught 2 divided by the sum. Rho 2 will be Z2 minus Z naught 1 divided by the sum. Rho 3 is equal to what? Who's going to help me with rho 3? Which one is Z1? I keep forgetting which one is 1 and 2. Yeah, Z1 in parallel with Z1 2 minus Z0 1 divided by the sum. Okay? So these are my rows. So if I start with 1 here, by the time it reaches here, it's going to be 1 e to the minus gamma L1. Which one is L1? Let's see, L1 and L2. L1 here. L2 there. So that's 1 e to the minus gamma L2. Right? I'm going to call e to the minus gamma L2 as transmission coefficient number 2. I'm going to call e to the minus gamma L1 as transmission coefficient number 1. Right? Just for the sake of convenience. So this is actually 1 times T2. 1 times T2. So that goes through rho 1. So what you get back here is rho 1 times T2. How much goes through here now? You fell in the hole. You fell in the trap. Who else is going to fall in the trap? Most of us do, right? You always think about minus. Why minus and why plus? those who thought he's wrong, show me that you are right. Why? Why is it plus?
You need the plus because the phase is determined in rho already, with whether it's minus or plus. So if it's plus, it would add on top of the incident wave. If it's minus, then it would subtract.
So why you add it instead of subtracting?
Because whether the incident wave and the one that's transmitted are in phase or not is already determined in the sign of rho.
That's the,
Hmm?
the incident wave and the reflected wave essentially are superimposed at the boundary.
Okay,
So, yeah.
why do you have it? Why not subtract them?
Because that's the total,
Hmm?
it's the value of the voltage wave or whatever.
Because energy is conserved.
It's all because the convention we used. Right? When we wrote the general expression, we wrote V of Z is V plus V minus. We assumed that, right? We said, let's superimpose them. You could have added any coefficients with any polarity you want, and let the boundary condition determine if they are positive or negative, right? We decided that superposition, naturally we add a plus, all right? So we started with that, and based on that we continue. There are other people that do it the opposite way, by the way, all right? If you ever see a reference, go with the minus sign here, don't discredit it. It's valid. I could have started with a minus. I'm just adding two random numbers that I have no idea what they are, and I'm going to let the boundary condition determine their nature later on. Because actually sometimes V minus comes out to be negative, even though I added a plus. The math is going to prove to me that it is negative. Right? It's an algebraic equation, and we chose to start with a plus. And the people that start with a minus, by the way, their goal is, you see, when we start with a plus here, the current comes out eventually with a minus, right? That came as a result of this. The mathematics proved that if you start with a plus, you come here with a minus. There are some applications that like to see a plus in the current. Some applications, they prefer to see a plus in it, so they start with negative voltage. That's the reason we are adding them, because we started our development with a plus, and therefore we have to be consistent with our first assumption. So it's actually an assumption that we are following, right? And it gets confusing because people say, well, I'm reflecting some of the signal, how can I get more? What are you getting more of? Only the voltage. You're not getting more power. Because actually, if you think about this, this is your voltage and that's your current, and if you multiply voltage by current, you end up with what? Something squared minus something other squared. Right? So you end up with V plus squared minus V minus squared. And that's power minus power, so actually you end up with less power. There's no way you can add power out of a reflection in a passive device. You must get less power, or equal power. Right? So the fact that you get higher voltage is very acceptable, because you have a step-up transformer that can step up your voltage. You start with 10 volts and you can come up with 40 volts on the other side, but you get less current, right? You get less power. So step-up transformers are there and step-down transformers are there. So this one here is a step up if the reflection coefficient is positive, and if it's negative, it's a step down. All right? So you end up with 1 plus rho times T2, and by the time you reach here, it's going to be 1 plus rho times T2 times another T1 now, right? That was rho. What you get back here is rho 2 times 1 plus rho 1 times T2 times T1. By the time you reach here, it's going to be rho 2 1 plus rho 1 times T2 squared times T1. T1 squared. When you get down here, rho 3 times the same expression. I'm going to put that square brackets and just write it like that. How much do I get here? 1 plus rho 3 times the square bracket. And so on and so forth. So if you look here now, and you want to write your V plus will be all the waves going to the right in this location. Say I want to write V plus, this is Z is equal to 0. So my V of Z is simply V plus plus V minus. So that's my V plus, the 1. That's the only wave that's traveling to the right. And the V minus is all the waves that travel to the left. The sum of all these. This is my V minus. Somewhere in here, your V plus e to the minus gamma z, whatever it is, right? I'm just going to show the waves traveling to the right is going to be the sum of, I'm going to mark them with x's, all the x's here. Sorry. Right. These are left. And the waves that travel to the left will be the sum of the check marks. You just add those expressions, they sum up to the waves traveling to the left. You want to get your gamma? In this case, gamma in this location is going to be the ratio between the blue over the red. Okay? So the gamma would be in terms of several expressions here that are those. While we are in this mode, let's do the Thevenin's problem this way. So the Thevenin's problem is that you have this fellow here, and you have an impedance here. We need to get the Thevenin's and V Thevenin's. So what do? We take this one out, put an open circuit here. Now to get the Z Thevenin's is easy, because Z Thevenin's will be the input impedance here when you short out your source, and Z Thevenin's will be this impedance. Z driving point impedance at this location, Z source, lambda by 2, that's always easy, to Z source side away. Right? A lambda by 2 line reflects the same impedance. So that was easy. It's a V open circuit now that takes some doing here. How do you get the V open circuit? It's V of Z at Z is equal to L in this circuit. You need V of L. You have Vs here, Zs there, and a line of lambda by 2. When people came to the office asking me questions about this, they were all trying to solve it up in the air. And when you are not up to that level yet, you shouldn't just start guessing, right? You better trust your math and just follow the math. Not like example I gave to them, don't take the shortcut before you know the wrong way first, right? You walk into a new town, right? You don't want to start taking shortcuts. You lose your way. So go through the territories and get the feel of things, and then when you are comfortable, you can start taking the shortcuts. So don't just say, a lambda by 2 line means it's not there. Or a lambda by 2 line is whatever, you know. Let's just do it. So you have a problem here, you want to find V of L, that means you have to solve V of Z, and solve Z is equal to L. So I need to get the expression. To get V of Z, there is two ways to do it. Either V plus e to the minus gamma Z, plus V minus e to the plus gamma Z, and solve for V plus and V minus. That means I need two boundary conditions, and the two boundary conditions are boundary condition at the source, and there's a boundary condition at load N. The other approach is to re-express this as V plus e to the minus gamma Z times 1 plus gamma of Z, and use the load end to get gamma of Z, and use the source end to get V plus. I'm going to do this one here. I'll say V gamma sub L is equal to open circle, right? So infinity minus Z naught divided by infinity plus Z naught gives me a +1, right? Reflection coefficient of +1 at the load. So gamma at the load is equal to +1. Gamma at the source end, gamma of 0, would be what? Gamma of 0 will be gamma at the load, e to the minus, I keep forgetting that, e to the plus 2j beta L. All right, if I put that in there, I end up with the same, L is equal to lambda by 2, and 2 pi, that's 4 pi over that means 2 pi, that means gamma L. All right? So I go to the source end now, and write expression V of Z, V of 0, V of 0 right here, is equal to Vs minus I of 0 times Z source. Okay? And V of 0 is V plus times 1 plus gamma of 0 is equal to Vs minus I of 0, which is V plus times 1 minus gamma of 0, right? Zs. And gamma of 0 is 1, so that's a 1. That means this goes to 0. That's the one, that means this becomes 2. All right? And that means Vs, V plus, is equal to Vs over 2. That means that was 10 volts, that means 5 volts.
I think your phone's leaving a message for somebody. It was talking.
Still talking?
I think it's leaving a message
Okay,
for somebody else.
that's all right. It's my niece calling from Canada. She should know the time better than that. People call from overseas, they get confused about the time difference. She's in the same time zone. All right, so that's Vs over 2. That means V plus is equal to 5 volts. Okay? That means I have the V plus. Oh, that's all that I need now, right? We need the V plus. So I go back and write my expression now at the load. V of L is equal to V plus e to the minus gamma L plus V minus e to the plus gamma L, right? Now, remember gamma of 0 is 1, so that should be V minus, if you wish, is equal to the same as V plus, Vs over 2, which is 5 volts. Right? So it's equal to 5 times e to the minus j beta L is what? Minus 1, right? Because you have a lambda by 2. And this one here is another lambda by 2. Get minus 10. Right? So that is how you get your V open circuit at the load N. Now, let me show you the same thing with a bounce diagram. Now, you may have done the V plus and V minus straight without the gamma. Whichever way you do it, you should end up with the same answer. Bounce diagram. I have a 10 volt here. That's Zs, Z naught. And I have a reflection coefficient plus 1. But I have a different reflection coefficient here. Let's call it rho S. Rho S is equal to Zs minus Z naught divided by the sum. Okay? Bounce diagram, I start with the signal, goes to here, bounces back, keeps on bouncing back and forth, right? So let's call the signal A. That becomes what? A e to the minus j beta L. That's a minus 1, right? So it becomes a minus 8 right here. It reflects in a reflection coefficient of plus 1. Rho is plus 1 here. So you still get a minus A. You go through another negative sign. The T here is equal to minus 1. That's really what made that A become minus A. So that is a plus A now. This one here is rho SA. This one here is minus rho SA. This one here is minus rho SA. Because the reflection coefficient is still plus 1. This one here is a plus rho SA. Every time you go through a line, you flip the polarity. This becomes rho S squared A minus rho S squared A minus rho S squared A. I guess it's very obvious, rho S cubed A. You can see things going into a pattern, right? So do you need VL? Which I can give you VL and V0, both of them. They can come out. Let me erase on this side. So V at L is simply equal to minus 2A. I guess I can take it as a coefficient. And I say 1 plus rho S plus rho s squared plus dot dot dot, right? Can you see that? So it's equal to minus 2a minus rho sub s. Isn't that a geometric series, and that's the sum of the geometric series? Done. I have the A. How much was the A? Was Vs times Z naught divided by Z naught plus Zs. If you work out things here, put rho s as Zs minus Z naught divided by Z naught plus Zs, you end up with what? Minus 2a. And you have Z naught plus Zs here. And you have that minus that gives you 2Z naught. And this one he gives you Vs Z naught divided by Z naught plus Zs. Oh, the A is already done. That's minus Vs, minus 10. Same answer.
One question on that one. What did you I0 as 3 plus 1 and 3 plus times 1 minus 1 is 1?
I'm missing divided by Z naught. You are right. Let me write that in color. All right? Correction. Divided by Z naught. Now, the bus diagram in the frequency domain, as you can see, is more fun than working out the math and the simultaneous equations that you had to solve on the other side. If you can master that, all right, you would have less trouble solving problems of that nature. Let's see V of 0 here. It's A plus A, if you wish, plus rho SA, rho squared SA. Wait a minute, that's still rho squared, rho cubed, rho S cubed is here. Okay, so as you can see, it's 2A plus 2 rho SA plus 2 rho S squared A, etc. So it becomes 2a divided by 1 minus rho s. If you notice, it's the same expression that we had here except for the minus sign. So it's actually equal to plus 10. Now, if you wanted to use the logic and the shortcuts, you could have said the following. You see, an open circuit here is going to reflect an open circuit there because it's a lambda by 2 line. Open circuit here means the current is 0 here. And if the current is 0 here, it means this voltage 10 is going to appear there. And we know a lambda by 2 line shows the same impedance on the other end, but the voltage repeats every lambda, not every lambda by 2. The impedance repeats every lambda by 2, but the voltage repeats every lambda. So lambda by 2 away, the voltage should appear negative of the voltage at this end here. So if you have 10 volts here, and the current is 0 there, similar to that, so the voltage here is going to be minus 10. Finally, say now Z Thevenin's is there, and V Thevenin's is known. You put ZL here, and you find the voltage here in the presence of the load. That's a simple voltage divider. I spent enough time on this to make sure that we cover all the hidden details. Now, the bounce diagram is also a powerful tool to get the S parameters. And that's why I'm encouraging you to practice that. And like I said, you won't find the bounce diagram in the frequency domain in many references. Actually, I remember seeing it once in one of the books, but I haven't seen it in any other books. But I've been using that for ages here, and I'm finding it very effective in solving things, because I'm one of the people that have less patience for solving simultaneous equations. I don't like it. You get confused and you may end up doing extra steps that are unnecessary. While this one here, you get everything. You solve the whole thing, you can get anywhere you want. If you want to get the voltage here, or the gamma, or the picture is in front of you, and you can sum the terms. You sum the proper terms, and you get what you want. Like, I want to get the gamma right here. So what do? Gamma input. Or gamma of 0. Huh? Who's going to help me with that? Waves traveling to the left. A plus rho SA plus rho S squared A divided by waves traveling to the right. A plus rho SA plus rho S squared A. Guess what? I know we have an easier way in getting it than that, but if this was not the case, if this was not a simple case like this, you have a tool to get those expressions. Here's your gamma of 0. Gamma of L would be, again, waves traveling to the left, here they are. Sum those, divide them by the waves traveling to the right. Divide by those. Sigma yellow, divide by sigma blue. Give you gamma at L, which is obviously, again, a plus 1. Right? So that was one of the hours out of the 3 that we need to solve the midterm in, right? I solved the rest of the problems in 2 hours. I didn't expect to take that long in this discussion, but I'm not regretting it. Any questions? We'll solve the rest of the problems on Friday. Hopefully I'll go through your papers quickly this time, and if things go well, I'll bring you by Friday. Do you have any questions about the project at this point?
When are you holding office hours this week?
Office hours this week. I have office hours today until 1 o'clock,
Okay.
and then on Friday until 12 o'clock.
Friday.
Tomorrow I'm out.
Okay. Friday 11 to noon.
Yeah.
Okay.
And yesterday I spent it all in doctor's offices, and I didn't look at my emails, so I apologize. There were a couple of emails that I discovered this morning that I didn't get to.